Welcome back. In this section, we will revise the most important linear algebra concepts that you will need in modal analysis. And it's also good to know them in general if you're involved with control engineering. So we left off with this transformed linear ODE. In linear algebra, there is a very useful application called diagonalization. This concept will decouple our system. Let's say that we have this matrix, and I want to diagonalize it. What does it even mean to diagonalize a matrix? It means that you will write it out in this form, where D is a diagonal matrix, where the entries in the diagonal are the eigenvalues of matrix A. And then matrix P is a matrix of eigenvectors, and those eigenvectors are organized in columns corresponding to their respective eigenvalues. So this eigenvector, it corresponds to this eigenvalue, and this eigenvector, it corresponds to this eigenvalue. Note that the order is important here. If your D was this one, so I switch the positions of the eigenvalues, I first have lambda 2 and then lambda 1, then that would mean that I would also have to switch the columns in the P matrix. So the eigenvector that I had here will now be here, and then this one here would have to move right here. It's important that you pay attention to this little detail. If you mix up the order, diagonalization will not work. Now, computing eigenvalues and the respective eigenvectors by hand for a 2x2 matrix is relatively easy. For higher dimensions, however, it's better to use software. The definition of eigenvalues and eigenvectors is the following. For a 2x2 matrix, it would look like this. So this is one of the eigenvectors of matrix A, and then on the other side of the equation, you have the same vector times a constant, which is the eigenvalue corresponding to this eigenvector. And in general, if you have a square matrix that has the dimensions of n by n, and let's call this matrix A again, then the square matrix A has special vectors called eigenvectors, such that if you multiply A by one of them, then on the other side you will get a vector with the same direction. And this is the key, the direction. That's why eigenvectors are special. This eigenvalue here, it's a scalar. It scales this eigenvector, but it doesn't change its direction. Let's say that I have this vector, and then for this lambda, let it be 2, then 2 times this vector would be this one. Or if your lambda is minus 3, then you will have this vector. In all three cases, we have the same direction. And here we are ignoring the positive and negative directions of the vector. So we don't care whether the arrow points in this direction or whether it points in this direction. The important observation is that all these vectors, they lie on the same line. That's what I mean by having the same direction. Whether the arrow points in this direction or in that direction, and by how much, is determined by this eigenvalue. But the eigenvector determines how this line is tilted. Another eigenvector could have given you this line. Another eigenvector could have given you this line. Another way of looking at it is like this. If you multiply your square matrix by a random vector xr, then you will also get a vector that we can call br, but xr and br will have different directions. They will not lie on the same line. So maybe xr lies on this line and then br lies on this line. The tips of these two vectors will not lie on the same line. But what makes eigenvectors special is that they preserve their direction after you multiply A by them. So you multiply A by its eigenvector, and let's say that this is your eigenvector, and then what you will get is a vector whose tip lies on the same straight line. So this would be then this vector, and then the eigenvalue determines where exactly the position of the vector's tip is on the straight line. If lambda equals 1, then of course that point will also be here. If it's something else, then that point will end up being somewhere else, but it will still end up being on this straight line.